Welcome to Rawson Connection, a podcast about all things Lehigh engineering. Coming to you from the P.C. Rawson College of Engineering and Applied Science at Lehigh University. It's a show for students, alumni, faculty, and staff, current, former, and future, and for anyone interested in the many creative ways that engineers are solving the world's problems. I'm your host and producer, Christine Fennessy. And yes, we are back. Regular listeners know that both the show and I went on a brief hiatus. Let's call it a sabbatical. I'm very excited to be here and to be bringing you a great conversation with Jim Gilchrist. Jim is a professor in the Department of Chemical and Biomolecular Engineering, and he's got a fairly new course that he'll be teaching this fall for first-year students. It's called Coffee and Cosmetics, Engineering of Consumer Products. The course made its debut over Zoom this past spring, and he'll be teaching it live this semester. And the title alone makes it appealing. I mean, coffee and cosmetics, half the course being about the elixir of life. But it's the story behind how that course was created that's really interesting. It took a pandemic, a whole lot of student ingenuity, and a pretty steep learning curve for Jim. On today's episode, Jim Gilchrist tells us that story. He also describes his research and what's so fascinating about how paint dries and why raisins don't just settle to the bottom of your cereal box, and how he tries to explain that fascination to his family. He also talks about how getting more students excited about and engaged in chemical engineering might just start with a cup of coffee. Thanks for joining us. Tell us a little bit about what kind of a kid you were growing up, and was there a moment you realized you were interested in engineering, even if you didn't maybe know what it was at the time?
Yeah, so when I was young, really, math was a passion early on. I liked the simplicity of it, that you could get concrete answers, whereas I was an avid reader, but I liked reading the things I wanted to read, not necessarily what other people wanted me to read. I picked engineering probably because I didn't necessarily have to take English in college, and I know that sounds horrible, but I was good at math. I was good at physics, so I wanted to be a math-physics double major, and then someone said, well, why don't you just pick engineering? I took a fluid mechanics class almost right off the bat, and that's all math and physics. So that's really where my passion landed quickly, and that's still what I do today.
And what was it about fluid mechanics? Why do you say that was your passion?
Well, it has this math concreteness and this physics that is so deep. When you think of a pendulum swinging back and forth, you know which way the pendulum's going to go. But when you watch water flow, it doesn't necessarily follow the way you would expect. And so there's this beauty to it, but it's this mathematical precision to it at the same time. And that combination I just thought was mesmerizing. Okay,
so today your lab is called the Laboratory for Particle Mixing and Self-Organization. So how do you explain what you and your team does to your family and friends who aren't academics, who aren't engineers or scientists?
Yeah, and that's tough. It's always tough. My family's always asking what I do, and I explain it, and they say, I'm not sure if I get that. But once in a while, things click. So I think the easiest way to start is that if you look at consumer products and raw materials, I think about 60% of all raw materials that go into making, whether you're making an iPhone or a computer or some sort of chemical process, 60% is particle-based. And so particles are, they can flow like water, right? They can be aerated. Like if you're at the beach, wind whips up the sand and it acts like a gas. Or it can flow like a landslide, or it can act like a solid when you're walking on it. It's kind of like a fluid, but we would call it a complex fluid, meaning it sometimes behaves like a fluid and sometimes behaves like a solid. And so I study a lot of systems that have particles in it. And, sometimes I'm just studying how they flow, because if you're trying to fill a rail car or some other container, you could use a funnel like you would for a fluid. But sometimes it gets jammed up, and that wouldn't happen with water, but that certainly would happen with grains of sand. So we study that, and we also study really small particles that they behave as if they're part of the fluid itself. Milk, a gallon of milk, what makes it milk is water with a lot of little fat particles, and how they flow around is very much of interest to milk production, for instance. How would you separate that out to make whole milk versus skim and so forth?
Well, that's interesting. And And also a good explanation.
Good. You never know. Sometimes I say that, and the lab name, particle mixing and self-organization. The joke behind that is that I studied mixing when I started. How to mix powders, and they don't like to mix. So if you have your typical cereal like Raisin Bran, all the raisins end up at the bottom, and the harder you shake, the more that happens. Whereas when you're stirring your coffee, the harder you stir it, the more it mixes. So there's a difference between fluids and particle systems. And so particle mixing and self-organization, the joke is if we're trying to mix, they sometimes self-organize, and sometimes if you're trying to self-organize, they mix. But we'll study whatever happens one way or another.
And is self-organization what happens in the cereal box?
Yeah, you can think of it as a separation process. Typically, the smaller grains or the heavier grains tend to move toward the bottom when you agitate or shake the system. You think a box of cereal, how complex is that? But if you're making rail cars of cereal, if you're a cereal producer, this is a big deal. If every box had all the raisins at the bottom, your consumers would be not very happy and pick another brand. So trying to figure out how to mix it in the first place. And I say cereal, you could think of like a pharmaceutical product. For instance, every pill starts out usually as a solution or some sort of mixture of dry powders, and they're packed together. And if the ingredients in that pill, let's say it didn't mix well, maybe one pill has no active ingredient and another pill has 10 times the active ingredient. Take any pharmaceutical product, not active would be bad, but 10 times the active ingredient might be horrible. So pill by pill for trillions of pills a year, it's pretty amazing what they can do.
Yeah. Oh, that makes sense. Can you give me a few examples of what you and your grad students are researching right now?
Yeah. So I think the one area that has kind of culminated into a focus area of my research was this idea of particle-based coatings. When I say coatings, I literally mean like the paint on your wall. So that's a latex-based coating, and it's complicated. If you start with a gallon of paint, it's a bunch of nanoscale and colloidal particles that are freely flowing around that liquid. And then you draw it into a thin film, and you hope that paint stays on the wall while it's a liquid and doesn't drip down. And then you hope over some relatively short period of time that it goes from a liquid state to a solid state and deposit those particles as like a polymer film. We do have a grant right now where we're studying paints formulated by PPG and collaborating with someone at Case Western, Chris Worth. And we're really trying to understand what is the change of behavior of that material when it goes from that liquid, when you are ready to coat it, all the way to when it behaves like a solid on your car. When you buy a new car, what's the first thing you look at? You walk around the car and you look to see if there's any defects in the paint, right? And even a small little ding, immediately you're turned off to that car on the lot. So the paint job matters a lot, even though when you really think about the function of the car, it's probably not the main thing you should worry about. But paint jobs matter. And we're really thinking about like coatings and how materials, again, go through that process, but then how can the particles be organized to give you different physical properties?
What's valuable about understanding the behavior of those particles in the paint? Like, what is the end goal kind of that particular research that you're doing?
Well, I think there are so many things we don't understand, and they can be really simple, like when you paint a formula that has particles in it, will the particles be distributed everywhere? Will they get stuck to the substrate? Will they end up at the top of the film? So we know some of that for some particles and some systems, but I'd say not in all cases, because it depends on how the particles interact with each other. They could be repulsive or attractive. When they're attractive, that's essentially what forms a gel. And so paint formulation may have dozens of components. And when you change the pH or the ratios of those components, the way the particles behave can drastically change. So there's a lot of that kind of very fundamental things, but there's also what's called structure color. And that is really about how nanoscopic particles and structures can reflect light to give you color. If you've ever seen like an opal, these beautiful jewels that have different areas of iridescence, there's no dye in there making it look orange or blue or green. What it is different angles of light hitting the different nanostructures that are in there and then coming back at your eye in different ways. So you see this in beetles, you see this in minerals, you see this in butterfly wings. And the next generation of smart and advanced coatings, really, they'll never fade. Actually, just today, I was cleaning out my closet a little bit this morning, some old shirts, totally faded. It would be great to have pigments and dyes that never fade. And there's not only something that's nice for the consumer there, but it also certainly is more environmentally friendly from that standpoint, that you're not using lots of different dyes and pigments. I've talked a lot about the optical properties, but the chemical properties matter just as much to protect the materials behind the paint. And a lot of these things, if you think of it as like a breathing membrane, so you think of like a Ziploc bag that is a membrane, but it was formed essentially using a coating process. And if you think about, can oxygen get through it? Can different gases or materials get through that? It can act like a barrier or a selective barrier. So labels for foods could tell you if there's bacteria inside by changing color or giving you some other indication. Or maybe you just make coatings that naturally degrade so we don't have so many microplastics filling up the oceans.
Oh, that's so cool. Okay, you've been at Lehigh for 17 years. So what have been some of the biggest changes that you've noticed over that time? Like maybe in terms of how chemical engineering is taught, or how students are learning, and or maybe what students are looking for?
I've said before that the equations we teach often are 100 years old. Things that were developed in the middle 20th century or before. So bringing that and making it fresh for students, I don't think was much of a priority back in 2004 when I started. I mean, I think day one, you'd come in, you're signed up as a chemical engineer, and they'd show you a distillation column and all kinds of process equipment. But they would really focus on those kinds of aspects, which on a day-to-day basis, you don't interact with those things as a consumer. I would say things have shifted now. So I teach the introductory chemical engineering class with Angela Brown, and we spend a lot of time thinking of analogies of how to introduce these tough concepts. It's chemistry, physics, and math used in a very new way for the student. But how do you relate these things that eventually will be applied to distillation columns and heat transfer units and reactors and so forth? How do you relate that to a student who's never been in a chemical plant? And so you can start the basics of like how your refrigerator works or how a coffee maker works. Instead of talking about relative humidity and talking about vapor pressure in some vapor liquid equilibrium in some container, I can talk about on a cold winter night when I go into a house that's warm, my glasses will fog up immediately. And why does that happen? It's because the glasses are cold. They cool the air. Go below the dew point and the water gets deposited onto your glasses. And those same equations that describe that are the same ones that tell you how a distillation column works. You have to kind of turn things around, of course. And it's a little more complicated than that, but not much more complicated than that.
Yeah, well, that makes total sense. Yeah, so how do you talk about a coffee maker in terms of using a familiar object to explain chemical engineering?
Oh, I mean, a coffee maker is perfect because I think a lot of people think I have a cup of coffee and I'm going to mix stuff into that coffee. But when you start with just the coffee, where did that come from? It comes from coffee beans, which are actually more like a pit of a cherry. And that was an agricultural process. But then there's also this bulk handling of these solids and so forth. It's very chemical processing, chemical engineering. But when it gets to your coffee maker, you have grounds that you're going to grind up. And the size of those particles tells you the difference in the surface area of those particles, and how is roasted. That is just a chemical reactor at its simplest bare bones case. And so you're roasting the coffee to bring out different flavors. You grind that up. That's all chemical engineering like things. And then you'd heat up water. So the process of heating up the water is very chemical engineering because that's thermodynamics. You transport that water up through this packed bed of coffee grounds, and you extract the flavors and the oils from the coffee into that water that eventually drips down into your cup. Essentially, every part of that connects with a class or a discipline within a subdiscipline within chemical engineering. And so in a lot of ways, you can actually just take apart the coffee maker and say, okay, this is how fluids flow and heat transfer. There are classes on that in chemical engineering. How the coffee was roasted, that's a reaction engineering process that we have a class for that. And then how things filter through and extract the essence of the coffee from the grounds. That's a separation process. And that's what we teach right before we get to the design class where we're designing chemical plants, but you can use the same principles to design a coffee maker. So it's a great place to connect students and people who don't really know what chemical engineers do, every part of the coffee maker really connects to the different parts of our curriculum.
That is a great explanation and a great segue into talking about your new course, Coffee and Cosmetics. So where did the idea for that course come from?
I would say the initial part of it came from the fact that there are other people out there using coffee in chemistry and chemical engineering to introduce design principles and the fundamentals of what they're teaching. So I can't say there's a lot of originality there. The cosmetics, I would say in my field, I study particle technology and rheology. Rheo is flow, so it's the study of flow. And if you go to a conference on rheology, you'll see people from the consumer care product area and cosmetics and so forth. Then they come because, for instance, your toothpaste, if it doesn't flow correctly, if it's so solid you can't get out of the tube, you wouldn't use it. If it squeezes out but then melts through your bristles all over the counter, you just be disgusted by it, right? So they really care about how things flow. And so they often are asking questions about formulations and how things flow and how to mix things and so forth. So during the pandemic, March of 2020 hit, we went away from spring break and we didn't see each other again for how many months? It was horrible. So come graduation, seniors left, a lot of undergrads lost their internships. And so the college started this, it was a 1-credit program, a free 1 credit. And you could do research with professors who could figure out ways to do this virtually. And my own research is experimental. It'd be very difficult. But I was thinking, these students have so much to offer. Why don't we get a focus group of chemical engineering students together and just ask them questions about how can we make our program better? Throughout the summer, they met with me once a week for a couple hours and then meet individually working on sub-projects. And all of this was really about how can we make Lehigh's chemical engineering program better? They came up with 4 ideas, and one of those is to design this class. It could have just been coffee, but out of the 10 students, 7 of them were women, and they said, "Oh, you must have cosmetics in here." I mean, it's such an easy way to connect with, well, everyone, because I put on deodorant and some lotion, whatever. But they then came up with this idea of we're going to develop a curriculum and pitch it to the department as maybe this could be a new class. So the class is entitled Coffee and Cosmetics, Engineering of Consumer Products. So the students, they love the idea of how can we make this into a course and not just what's the content, how does a coffee maker work and how do cosmetics, how are they blended and what are the ingredients and what's the chemistry, and there's what we also call interfacial science that's an important part of that. But they really want to talk about how do we get the students involved? How do we make modules and labs where the students would be hands-on, they'd be engaged, and they ran away with it. It was great.
Oh, yes. Well, and so the course is about the engineering of consumer products. So who is it for exactly?
Anyone. So we promise to not have anything beyond high school math, physics, and chemistry. Yes, pH is going to get mentioned, but I'm not going to make you memorize an equation and then spit it back on a test. It's really going to go into a project that you develop. So we start with a basis of things that you might be interested in. Say, okay, here's a project that you could do as a midterm or a final project, one on coffee, one on cosmetics. And then you take it in your direction, but there should be some of the things we learn from chemical engineering, surface science, rheology, and so forth that I'm going to introduce to them. But we had everything from high school students to seniors, business majors, finance majors, through some chemical engineering students took it. And it was great because we got a lot of different perspectives. But I also learned a ton from the business majors, like this idea of design a product. Maybe the chemical engineers would spend more time on developing the process, but the business students talk about thinking about marketing and how do you connect with consumers. It was really creative. And the students, the presentations, some of them are on our website. I think anyone who'd watch them would learn something about either how would I start a business, my own coffee shop, or how would I develop a new product, like why don't they brew coffee like they do tea? Why don't you just put in a little baggie and dip it in liquid? Well, part of the reason is coffee is more oily than tea, and it would just coat the inside of the bag with oil, and you can't get as much of the flavor out then. So they were thinking about how do you design tea bags for coffee that would stop this from happening.
You mentioned that the students came up with some modules. Can you give some examples of a couple that you did this past semester?
Yeah, there's student Brandon, who is one of the designers of the course and then became an undergrad TA for the course. he had said he was using something called Jamboards. It's a Google product. And if you think about maybe how business class works, where you might have a pad of paper at the front and everyone takes a marker and writes these crazy ideas on it or puts a sticky note on it to like get a lot of different ideas in one place and then work through a process of refining that down to its essence. But in this case, for instance, what types of coffee exist? And they might say regular drip coffee. They might say iced coffee, a frappe junior, mocha, a double espresso. And then I said, okay, everything that you just discussed, I want you to move the sticky note to the left if it's really a different product because of the ingredients, or move it to the right if it's a different product because of the process you used. So for instance, a cold brew, it's not a different type of coffee. You just brewed it a different way. So that's a process. Whereas a mocha, for instance, you put chocolate in it. That's about the ingredients. And then I asked the students to think about, what do you think from a physical or chemistry processes, what exists when you make coffee? Then they started realizing, well, there's also things like, roasting, decaffeination, drying, fermentation, harvesting, the collection of the beads and transport, and of course, filtration. And then someone actually even put pouring a cup of coffee. And then I asked them to put that in order of what are the first things you do to the last things you do. And then I just started circling areas. Well, this is agriculture. And this is transport, roasting is reaction engineering, and then the brewing process is a separation process, and then mixing for adding different ingredients, and just broke it out into the different areas of chemical engineering that would agree. They always thought of coffee as a product, but it's actually a process, if you think about it. It's a multi-billion-dollar process. And then I let the students put a sticky note by the areas they wanted to learn the most. And so a bunch put sticky notes by the environmental side and the harvesting. And then there's a lot of students who want to know about the roasting, less about the grinding, and then a bunch about like the extraction process at the end. And so that's what we did. We broke up the lectures from there on into exactly what they chose.
So the students in your focus group, they proposed starting with this module that would then yield interest areas amongst the students in your class. And is that how you proceeded this past semester?
Yeah, absolutely. This idea of choose your own destiny, what are the student interests? And it turns out one of the students in my first class actually is from Guatemala, and his family owns a coffee plantation. And so I felt very intimidated, and I believe he was an industrial engineering major, and his father is a chemical engineering major. And his father was always saying, you don't understand this because you didn't do chemical engineering. Well, he felt so good about taking this class because he would go back and have these conversations with his father about, now I understand what you mean by extraction. Right? Now I know what you mean by these different things that you've talked about. But if the whole class was just business majors, it would have a different flavor, or maybe it was just students who were really focused on the cosmetics. Maybe we'd spend an extra week or two talking about cosmetics instead of coffee.
Wow. So it sounds like it's kind of like a living curriculum in a sense.
Yeah. And what's great is the students, when they did their projects, I learned new things. I think of it like a snowball where you start with a small seed and then it rolls and it's going to get bigger. So it was a bit selfish having these projects because these projects will become lectures in the future.
Wow. And so is the idea that you also would have a module around cosmetics and then you learn what the students want to learn around cosmetics?
Right. Halfway through the semester, after the students did their coffee midterm presentations, we started right from the beginning again and said, okay, what kind of cosmetics are you familiar with? We actually broke it down into, is this something that is for beauty or maybe cultural significance versus something that's more health or pharmaceutical related? For instance, today I put on deodorant. I'll admit there's something cosmetic about that. I don't want to smell. Fine, But on the flip side, I used some hand cream and facial cream so my skin doesn't get dry. That's definitely more on the side of health, right? If you think of drug delivery and so forth, there's a lot of cosmetics, things you apply to your skin that are really about delivering a chemical as opposed to changing the way it looks. So we kind of broke things up that way and then started talking about what's important in each part of that. So maybe on the cosmetic, how things look, color, fragrance, texture, ease of use, packaging. And on the pharmaceutical side, are they all natural ingredients? Is it eco-friendly, but also is it going to be irritable to your skin? Benzoyl peroxide for zit cream. We talked a lot about zit cream. And it's about delivering a chemical. And so we did that. And then I did give like a traditional lecture on skin is the tapestry in which you're using. So you start with a substrate and you're putting a coating. And my research is about coating. So I always said coffee is a lot of chemical engineering. Cosmetics ends up being very much related to my research. And that's where I can connect with both.
Yeah. And so was this past spring the first time that coffee and cosmetics was offered?
Yes. And the students actually made a pitch to the department. Can we have this class? And they came to a faculty meeting, and all the faculty really received it well. But I'm sure that was intimidating for the students, and probably not something that happens commonly where the students are proposing a class for their own curriculum, right? This is just like in the class itself, they're kind of designing where they're going. And it's the students who really came up with these ideas. I facilitated it, but they were so engaged. And 7 of them were undergrad TAs, and I would message them through Slack and say, hey, am I doing this right? And the students would say, yeah, that's great. Or that's great, but that's not the way we discussed it. And why don't you try something else? And I definitely listened to them. For me, it was daunting. It's a shelter for me to teach a bunch of equations I know. Even if I find creative ways to do that, I'm still kind of in charge. I kind of am the expert in the room. Whereas in this case, a lot of times the students in the class became the experts in the room with knowledge beyond my own. And the TAs certainly did that when they designed the class with me. And now the students that are taking the class. And that's what I've learned most is asking the students what they know before I tell them what I know.
And so coffee and cosmetics is being offered this fall, correct?
Yes, coffee and cosmetics is offered this fall. If you're a first-year student, please sign up. We're going to be running it live. I don't know a lot of the details except that it's Tuesday, Thursday afternoons. And because it's live, we are going to have some hands-on components where we're going to have USB microscopes to investigate the materials, or brewing some coffee, making your own lip balm. It's going to be very different than running it on Zoom, but I've also invited all of the alumni from our class that have taken it before. If they want to stop by to get a free cup of coffee, try some lip balm, or just peek to see what the class would have been like if they weren't on Zoom. And some are actually signing up to be undergrad TAs for the next class, which is awesome. I need all the help I can get.
So what's been your biggest takeaway when you think about how it was really this focus group of students who were responsible for creating this course? What have you learned about the value of student feedback? And do you think what you've learned might change how you teach?
I think we need to listen more. There's always been this barrier between what we're teaching in class and then what the students are thinking and doing outside the class and so forth. And what I've learned was that I will be a better professor if I can learn more about what each individual student can bring to the classroom. That would be pretty hard in a classroom of 300, but luckily we don't often have classes that are that large. But even the ability to just break it down to smaller groups, or even have surveys to ask students, how do you feel about things? What is your background? What do you know? What would you like to learn about? What is most confusing at this point? Tell me what you think when I say X, and just letting them talk. I never did that before. Maybe I'm embarrassed to say it, but I am learning a ton about being a better teacher by listening to my students and how they're interfacing with the subject and life in general.
That's it for today's show. You can find a lot more information about coffee and cosmetics, engineering of consumer products, and watch some of the presentations that students gave this spring. Just search Gilchrist Laboratory. That's GILCHRIST Laboratory. And we'll have the link on our show page. Jim says this semester's class will also feature a competition to see who can brew the best coffee and make the best lip balm. For more information about academic programs at the P.C. Rawson College of Engineering and Applied Science, and to find our show, head to engineering.lehigh.edu. Music in this episode is by Blue Dot Sessions. You can subscribe to Rawson Connection wherever you get your shows. And send us story suggestions or feedback on Twitter @Rawson Podcast. Thanks for listening.